comes to your mind is that, well, why this is going to work fine? Why this is going to get the kind of different test samples, and then you're going to generate the right answer to that. Because for question answering, that's quite intuitive. Answer is, I mean, in general, a kind of right completion to the question. But for some other things, this is not the case. For instance, if it wants to classify a text, then this sounds like a different problem. The point here is that when you are training or pre-training a language model, it's like you are learning a kind of, as I told you, a generic distribution for the language. And typically, any language test that you have is somehow represented in one way or another with that distribution. Now, to understand this, I have made this kind of, in visualization here, but this is just visualization, so it's not a very concrete description of what is happening. So it's just to give you an idea why this is really the case that language models are so powerful then. So the point here is that when you have a language, any kind of, when you get your whole text or whole corpus, this one is including lots of different texts, right? Some of them are answer to questions and answers, right? Some of them are that there are inference or conclusion on a text, so they are somehow understanding the text, right? Some of them are about literature, some of them are about math, things like that. And now you can think of every single kind of task in language as one particular distribution. So what does it mean? So what do I have here? You see this distribution here. And by that is, this is space here. And by that space, I don't really mean a two-dimensional space. I mean huge dimensional space. Every single of those Q's is a distribution. And do you have an idea how I can show a distribution in a space? Any idea? If I have a random variable which has only two possible outcomes, what is the distribution of that random variable? It's a vector of size 2, right? Probability of the next one happening, probability of the second one happening, right? So I can show it as a two-dimensional point, right? In the space, correct? Now if I have another distribution, it's again a two-dimensional thing, but it has different values, right? So it's going to be another point in the space. But for your language model, that is not two-dimensional. That is trillions of dimension, right? But imagine that this is the space of the probabilities, right? So one of these Q's is just representing one task. Maybe this is question answering. Another one is just text classification. Another one is similarity checking. Okay? Each of them is one task, and for each task, we have one specific distribution. Yeah? And then I am thinking of those distributions of the language. It's true that they are different, but they are very close to each other. Because if you want to complete a text, you need to understand the context, right? Same thing when you want to classify a text. You again need to understand the context. So essentially, they have the same behavior, but the final output they are giving you is following a bit of different distribution, right? So now, when you start with totally untrained language model, so when you initiate the weights of your transformer totally randomly, this is giving you a distribution which is total nonsense. It has nothing to do with the language. You just generate random words after each other, right? And it's not useless. And then you do the pre-training. What you do when you do pre-training? You essentially push this guy somewhere in the space of these distributions, right? But that distribution is somehow containing the superposition of all these tasks, right? Because inside your distribution you had question answering, text classification, similarity check. For every of them you had a bunch of samples. They were coming from those task-specific distributions. And now what you have trained is a superposition of all of them, right? This is the generic distribution that your LLM learns. And this is the idea of completion. Because completion doesn't specify the task. It tells it, just give me a coherent text, right? And this coherent text could be the response to a question, or it could be a response to a similarity check, right? It could be both of them. So you are somehow training your model to behave a superposition of both, right? Sometimes it gives you answers, sometimes it just checks the similarity, sometimes it just gives you more information about that text, right? Now, what is going to happen if you want to have a specific test? You're going to focus in one particular distribution, right? So you would say, I want always to give an answer to a question. So it means that I'm not anymore looking into this general distribution. I want to mimic that distribution, right? But that distribution is not far away from this green distribution. Because the red distribution was one of the components making this distribution, right? Within my data set, I had lots of samples, questions and answers, right? Definitely I had them. This is a part of the corpus I have trained my large language model on, right? So when you are doing fine-tuning, you essentially push a bit your distribution towards that point, right? And this is not a hard thing, because I am showing everything here by exaggeration, but this gray point is essentially somewhere millions of, I don't know, light years away from that one. Yeah? This is far away from the other guy. Now, when you have done pre-training, you have done almost all of the way towards the distribution you want. The only question is that which test you want to do, and then, well, I'm going to find out that test. I do fine-tuning, so it's going to push me a bit further, and I'm going to get exactly the distribution that I want. So you get the idea of what is happening here, right? So it's not a kind of weird behavior that this model is not capable of doing many things, because essentially it has been trained to somehow do all of them, right? Completion of a text essentially means that answer questions, understand whatever is inside that and classify it, check the similarity of a couple of sentences in a text, all of them, right? So it has learned all of that. You're only asking it, making it to just do the particular task that you have in mind right now. Okay? Yes?
So the untrained point at the very bottom,
yes.
that's not a part of the graph, basically, right? Like, it's not trying to say that that point itself is very far from any of the Q-tip distributions, but rather it takes that and it maps it to a location within that space, right? After you use the pre-training.
Actually, as long as you have a language model, even if you start with a random weights, it's going to give you a distribution, right? So it is in the distribution space, but it's far away from the right distribution, right? Yeah, so you can't, distribution is always inside a simplex, right? So, huge dimensional simplex. And you can think this is the huge dimensional simplex, and your initial point is just a random point there, right? But your language distributions, all of those distributions, are compacted in a very tiny point somewhere in this huge space. And the chance that you start anywhere close to that is almost zero, right? So you're going to start far away from that. And by pre-training, you get to that tiny subspace. And now when you do fine-tuning, you just choose which direction you want to go.
Right, like in this space, when it's untrained, like in this example, we're not showing it here, but there are other Qs. Like
Definitely, yes.
right around there, yeah.
Yes, exactly. Yeah, definitely there are some distributions, but they are not language distributions. There are some dummy distributions, right? Because IID distribution is again a distribution, right? Every single word that I generate is randomly generated. This is another distribution, right? But this is not a language distribution, definitely.
Right, like what is the Q, I guess, right? Like this in this case, the Q is after being trained.
Q is after being trained, yes. Then you focus on a Q, right? Right.
Yeah, so it's kind of like saying with that bottom grayed out P, right? That would be surrounded by different distributions.
Yes, exactly. Yeah, which have probably nothing to do with language.
Yeah. Would you say, like, from like a visualization standpoint, though, like, are those other variables? Can you think of it as a separate space of the Q space, or is that?
Oh, I see. It depends. Yeah, it depends. But the point is that nowadays we think that it's a very philosophical question. Yes. Yes, yeah. This is a good question. I cannot give a concrete answer to that, to be honest. But the point is that, like, my feeling is that there is probably a tiny subspace which is everything that we need. Like those things are, because of the idea of the method of type, right? It's hard to explain it right now, in a short time. But my feeling is that the Q space is compact and anything out of the Q space is useless. My feeling. But maybe I'm wrong. So I'm not super expert, so I can answer. Yes, yeah. Yeah. Yes. Okay. Everybody's clear about this idea? So as I said, this is just intuition, but it's going to help you understand why LLMs are working so fine, right? Now, another way of looking at things, maybe it's easier for you instead of thinking of the probability space, thinking of the token space. What it means, so again, I have a space here for you, and this is again not a two-dimensional space. I'm thinking of the space of possible token sequences, okay? And token sequences, it means like any sequence of tokens could happen in this huge space, right? So one token sequence could be, how are you doing? This is fine. This is a right token sequence, but one other could be you am potato, right? This is just randomly generated, right? You has nothing to do with am, potato has nothing to do with the others, right? But all of them are the sequence of tokens, right? So initially when you are starting with an untrained model, it's just shooting any sequence. It can generate pretty much any sequence in this huge space, right? But what you know is that in the language, not all of those sequences are valid, right? A lot of sentences I can write here right now, and they have zero meaning, wrong syntax, right? So you immediately cancel all of those sentences, all of those sequences in your mind. And you're going to end up with a subspace, a small space, where only the right sequences are there, right? Any wrong sequence is not existing there. Yeah? So a right sentence is belonging to this space. So this is the space of sentences which are meaningful, coherent, but anything out of it is non-coherent. We do not use it in real language, right? So when you are doing fine-tuning, you're essentially pre-training, you're essentially making your untrained model to focus on those sequences, right? To sample from that space. So it's going to sample one coherent sequence. This is what you're doing when you are doing pre-training. But then you want to do one specific task. You want to answer a question. And again, anything in that question, answer of the question, is a coherent sentence. So that guy belongs to the same space, but it's not covering the whole space, right? So it's going to be a smaller space, correct? So there is a one subspace of these possible tokens, which are the valid answers, right? And what you're doing by fine-tuning, you are just playing around with those ways a bit, somehow to just focus on that particular subspace. Now I just want to sample answers. I don't want to sample any coherent sentence. Clear? So, moral of the story, when you are doing pre-training, when you make a language model complete a text, you have done 90% of the job. The remaining 10% is quite easy for you to do, because essentially you are in this space where everything, textual at least, is working. Yeah? The only thing is that you somehow figure out, this is a very powerful model now. Just figure out how you can convince it to generate the right output. Questions? No question? Okay, great. So if you got no question, then a few notes on the kind of fine-tunings that you can do. So in the general formulation that I told you, we thought of it, what we call it full fine-tuning. And what I do mean by full fine-tuning, I mean that you go over every single layer inside your large language model. So inside that transformer, every single layer which is generating keys, queries, values, feed-forward layers, everything there. And you just update all of them when you are doing the fine-tuning. Okay? So if you do, I don't know, 3 epochs, and in each epoch you have 100 batches, so it means that you are doing in general 300 iterations, and you update all of the weights 300 iterations, right? So this is the full training, but it sounds a bit full fine-tuning. This is a bit expensive, right? Especially if the model is huge. Sometimes you do know that really you don't need to spend this huge amount of computation, because essentially the information is somehow hidden in some, it's a tiny bit of change in your distribution to get into the right distribution. So if that is the case, then you don't need to really do the full fine-tuning. You can do a selective fine-tuning. And what do I mean by selective fine-tuning? I would just focus on a specific layer or a few layers. And I don't update everybody. Meaning that, for instance, I assume that, okay, everybody here, the embedding guy, the multi-head attention, self-attention layers, I don't know, the feed-forward layer, all of them are fixed. So I'm not going to update them when I'm doing the fine-tuning. The only guy that I'm going to update is the last layer. If I do know that my model needs a tiny bit of push to get to the right output, then I don't need really to go for the full complexity fine-tuning. That makes sense. Does it? Yes or no? OK. So this is selective fine-tuning. This is better when you know that, for example, the test that you have is very close to the original, text completion that you had. Like as I told you, question answering is not that far away from it, right? You just need to make your model start to understand that it's going to just answer, right? And then it's going to generate it. So probably you don't need to fully update all the weights, right? Especially if your model is huge. So this is selective fine-tuning, and essentially what you do in fine-tuning, you again update with the same number of iterations, but in each iteration you are not going to update all the layers. You just focus on one subset. So by this set W, I mean a subset of layers. You just focus on one subset of layers, maybe few layers, maybe the last transformer layer and the feed-forward layer, which computes the probability, and then you just fine-tune on those ones. OK? Everybody's clear? Questions? Yeah. That is the problem. It's quite of art. Like you need to play around with it to get the idea. Yeah. Questions? OK, no question. So one extra note I want to give you here is the idea of LoRA or low-rank adaptation. So nowadays, for many large models, we are not actually even doing this. I mean, it doesn't matter if you are doing full or selective fine-tuning. At the end of the day, when you want to update one layer, you're going to update all the weights inside the layer the same way, right? So you're going to look at every single weight. You're going to compute the gradient with respect to all those weights, and then you do gradient descent, right, for multiple iterations. But the point is that it has two problems. The first one is, again, the complexity problem. So you might have a very large layer, and this is going to happen in practice. And essentially, sometimes you know that you don't even need to complete all the weights there. Yeah? This is one point. So you don't really need to go for the complete complexity here. And the other thing here is that the second one is the fact that sometimes if you just do naive update of the layer, you might get lost. And what do I mean by getting lost? It means that you start with doing fine-tuning, so you do iteration, and at some point you start to get large gradients. And when you get a very large gradients, then every weight is going to just change hugely, right? So that layer is going to just diverge to a point where it's going to maybe do the specific task that you're looking for properly, but it's not capable of doing what it used to do before, right? So that powerful large language model that you built is now gone, and then you have, again, a task-specific model, right? Which is OK if you're happy with that, but essentially you don't want this happen, right? So you want your model to keep its power, only get more focus on the task that you want, right? And because of this, people came up with the idea of low-rank adaptation. They said, like, maybe we do not naively update everything. Maybe we use an alternative way of updating. And the approach is not very complicated. So what they do, they write down the updated weight in this form. Okay? Now, this weight here, so don't read anything. Just look at this equation here. This W here that you see is your layer. It means that it has k different inputs. A vector of size k goes in, and d goes out, right? What is the size of this guy? D times k, right? So it has d times k different variables there, right? If you want to naively update it, what you're going to do? You're going to compute the partial derivative of your loss with respect to every single of them, right? So d times k different partial derivatives, and then you update, right? Now, what they do here is that they do not touch W. So W is the one which you got in the pre-training, okay? So it's fixed here. Now they're going to write the new weights, which is the fine-tuned weights, it's going to be the previous one plus v times u. And what are these v and u? V is d times L, so it's a very, if you want to think of it, L is usually very small, so V is going to look like this. D is very large, so it has not so many rows, but it has a few columns, right? So here is D, here is L. And U is L times K, so it's now a very fat matrix, so it's going to be of this form. So it has K different columns, only L different rows, right? Okay? And now if I multiply V to U, this guy is U now. If I multiply this guy, V to U, what's going to come out of it? D by K again, right? So it's going to be D by L times L by K, which is going to be D by K, right? So V times U is having exactly the same dimension as W and W tilde. But the point is that, both together, they have less number of parameters, correct? Because if I think of this to be very tall and this to be very fat, then they're going to be, one order of scaling less as compared to that one, right? In the most extreme case, you can put L to be 1, right? Then the number of parameters is D plus K, whereas in the original case, you need to compute D times K different variables, right? Now, they think of the new ways to be in this form, and then instead of updating W directly, they are going to just update V and U. And when they keep on updating V and U, each time that they update it, then the updated W is going to be previous W plus V times U, right? And the reason they call it low-rank adaptation, because that V times U is a low-rank matrix now, right? It has significantly lower rank as compared to the complete W matrix. Everybody's clear? So the idea here is that you start with a bunch of initial U and V. You can start with 0. 0 is a kind of intuitive choice, because when it's 0, it's exactly the pre-trained version, right? And then you gradually update them. Each time you compute their gradient, and you just do one gradient descent. Questions? So low complexity, I guess it is now clear for you why we call it low complexity approach, because the number of parameters that we are updating in every iteration is significantly less, right? So in the original one, in the complete approach, I need to just update D times K different parameters, whereas in this case, I need to, how many parameters I need to update now? DL plus LK, right? So I can write it down in this form, L times D plus K, right? And it's not hard for you. Just think of D and K to be in the order of thousands, and L to be in the order of, I don't know, few, like less than 10. Then you can see how much different they are going to get, right? So this one is in the order of million, whereas it remains in the order of thousand, right? So significantly less parameters you're going to have. So in practice, the original paper proposing LoRA is showing that for many large models, even with L equal by 4, you're going to do a good job. Okay? But you can go above that, and then you don't need to go to the full complexity. You just get into, I don't know, 40, 60, then it's going to just perform exactly full complexity. And they do lots of empirical analysis to show that really they only need this low rank update. They don't really need the full update. So just to give you a bit of sense about the numbers, I told you that GPT-3 has 175 billion weights. And if you want to do the full fine-tuning with the complete updates, it means that every iteration you need to update 175 billion parameters, right? But if you use LoRA instead for every layer, so you update all the layers, but every layer that you want to update, you don't update with a classic or basic approach. You just use low-rank adaptation. Then the number of parameters that you need to compute gradient is going to significantly reduce. And this is going to be in the order of few millions. In the extreme case, of course. You can go higher, but in the extreme case, like L equal by 4 or something very small, this is going to be a huge reduction, and the performance is very tiny bit change in the order of less than 1% accuracy. And this is a great achievement, because this is going to help you even fine-tune your model faster, right? So this is, I mean, there are a bunch of other approaches out there for indirect fine-tuning, but LoRA is the most popular one because this is quite effective, and it has a bit of empirical justification why this is working. So, questions on LoRA? No question? So one thing that I want to make clear here, that LoRA has nothing to do with the full and selective fine-tuning, and you get it, right? Everybody's clear about that? When I'm talking about full or selective, I mean that whether I want to update all the layers or few of them, right? But in LoRA, LoRA is just telling me how I can update one layer, right? If I want to do full training with LoRA, full fine-tuning, with LoRA, I'm going to apply LoRA to all layers, right? If I want to do selective fine-tuning with LoRA, I'm going to select a few layers, and then again, I use LoRA to update them, right? So, everybody's clear, right?